There are two hydration reactions where you add a hydrogen and an OH. That's really HOH or H2O. And so when you add water, just like if you drink water, you're hydrating yourself. If you add water onto a carbon chain, you're hydrating that carbon chain. There are two ways to hydrate a carbon chain that carry over from alkenes into alkynes, carbon to hydrogen, hydrocarbons that have a triple bond, alkynes. Those are acid-catalyzed hydration and oxymercuration, demercuration. Now, when you first do these, as you know from the alkene chapter, they add H and OH in either a Markovnikov way, as in the case of acid-catalyzed hydration, or an anti-Markovnikov way, in the case of hydroboration oxidation. So that tells you where to put the H and where to put the OH. But if you compare this original molecule with what you have after you add an H and an OH, you don't see an OH anywhere. You see a double bond to an oxygen. And when you compare the same thing with hydroboration oxidation, you add an H and an OH, but you don't see the OH anywhere. You see an oxygen to a double bond. And it turns out that before you make these final products that are listed for these reactions, you really make something else first. The thing you would expect based on the reactions you learned in the alkene chapter. And that is that you take away just one pi bond. So you go from having 2 pi bonds, three bonds total, to just 1 pi bond, 2 bonds total, and you add the H and the OH. Similarly, for hydroboration oxidation, you take just one of the 2 pi bonds away. Now there's just that 1 pi bond. Remember, every bond after the first bond is a pi bond. The first bond you form is a sigma bond. And if this is anti-Markovnikov, the hydrogen goes on the more substituted carbon, the OH goes on the less substituted one. So that's what you get first. But if you compare that to the final product that you get, you'll see that they are similar, but they are not the same. The oxygens are in the same place, they're on the same carbon, but a hydrogen is taken off of it, so that the OH turns into a double bond to an O. And you'll notice that over on the right, where there were just 2 hydrogens, here in this molecule there are 3. And so a hydrogen gets added there. So it gets taken away here and added at the bottom there. So what's happening to transform this molecule that we first get into the molecules we end up with? That's what Keto-Enol Tautomerism is all about. Now that's a mouthful, so let's talk about what those words mean. If you look at this molecule, one of the products that you get after you do, for example, one of these hydration reactions onto an alkyne, you'll notice that you have a double bond, and you also have an OH. As we know, the infix for double bonds is En. And an OH is another functional group. That's a group of atoms that always functions the same way, no matter what carbon chain it's on. And OH is an alcohol. So for example, drinking alcohol and rubbing alcohol are not the same molecule, but what they have in common is they both have an OH on them. That's an alcohol. And the suffix for an alcohol is OL. So a molecule that has an alcohol, an OH, bonded to a carbon in a double bond is called an enol. If you compare that with the final molecule that we get, that we have here, in that final molecule we have a carbon double bonded to an oxygen with a carbon on both sides. And that is a different functional group, a group of atoms that always functions the same way. That is called a ketone. We saw that in the alkene chapter for the first time when we did ozonolysis of alkenes. Those would form either ketones, aldehydes, or a mixture of the two. So when you first do these hydration reactions, you get enols. But the enols quickly change either into a ketone or into an aldehyde. An aldehyde is like a ketone. You have the carbon double bonded to oxygen, but instead of being bonded to carbons on both sides, an aldehyde is bonded to a carbon on at least one side. Okay, so the enol and the ketone interconvert. And if you notice, the only difference between these two is the placement of one hydrogen. The enol has the hydrogen on the oxygen, and the ketone has the hydrogen right next door to the carbon bonded to the oxygen. So the only difference between the enol and the ketone is the placement of one hydrogen. And the relationship between two molecules that only have a difference of the placement of one hydrogen are tautomers. Tautomers are two molecules that only differ in the placement of one hydrogen. So, when you do these hydration reactions, the first thing that you get is an enol, but then that tautomerizes. It changes the position of one hydrogen to a ketone. And so the whole process is called keto, for ketone, enol tautomerism. It's a really important term that can kind of just be thrown around, and you should know what it means. It'll come back in organic chemistry too. Keto-Enol Tautomerism is where a hydrogen changes places from the oxygen to the carbon next door to where the oxygen was bonded to turn the enol into a ketone. So keto-enol tautomerism. Okay, now that can happen through an acid or a base catalyzed mechanism. What you'll want to know for this test is the acid-catalyzed mechanism for keto-enol tautomerism, at the very least. So how would that happen? How could this enol turn into a ketone? And notice that this is an enol. You have a double bond, so ene, actually, that's ene, and then you have the OH. That's the functional group, the group of atoms that always behaves or functions the same way. That's the functional group called an alcohol, the suffix for which is OL. So you have a ketone and an alcohol. How can that tautomerize? I'm sorry, you have an alkene and an alcohol. How can that tautomerize to give you a ketone? Okay, well, if you compare, we just need to take this hydrogen off of that oxygen. That's going to be a proton transfer, and we need to put a hydrogen on to that carbon. That'll be another proton transfer. So this mechanism really boils down to just two proton transfers. So I'll draw this out. That's what we have. Now, in the presence of acid, and our poster child for an acid is just going to be hydronium. If you put any strong acid into water, it gives its H pluses away. The water accepts them, and the water turns into H3O+, hydronium. Now, we've seen what happens in this kind of a situation before. Remember the mechanism for acid-catalyzed hydration in the alkene chapter. In that case, the double bond is a ketone, is a nucleophile. There's a lot of electrons there, and the hydrogens here are losing a lot of electron density to that oxygen, so they're all slightly positive. So when these come into contact with each other, the electrons in this nucleophilic pi bond attack the hydrogens, and they snap back onto the oxygen to stabilize the positive charge. Notice that what's happening here is a proton transfer. The same exact thing as the first step in acid-catalyzed hydration that we learned in the alkene chapter. So Once you have that, you will have this intermediate. If you think about where the hydrogen would add, because these electrons are on two different carbons, this carbon on the left and this carbon on the right, so where does this hydrogen ultimately go? It goes to the less substituted carbon, so that you can form the more stable, more substituted carbocation. But notice that here you have lone pairs next to a positive charge. That was one of the 5 resonance patterns. So you're really going to have a resonance structure here, and to communicate that, you'll draw these big brackets, and the brackets are warning people the true structure is none of the structures inside here. The true structure is only the average of all of them. And you'll draw this special resonance arrow with the 1 bar and the 2 heads, and that's telling people take the average of the 2 structures on either side. And when you have this resonance pattern, you'll remember that the curved arrows are that these lone pairs go toward the positive charge. And that should make sense, that these lone pairs would be drawn to that positive charge. These are electrons, and electrons have a negative charge, and opposite charges attract. So the structure that we'd end up with after that, after you move those electrons around, is that. Now notice this oxygen has 3 bonds here, and so if you calculate the formal charge on it, you'll see it's positive 1. In general, whenever oxygen has 3 bonds, it has a positive 1 charge. So those are our 2 resonance structures here. And you could almost see the ketone in this other resonance structure. The water that you get after the hydronium gives away its H+. That water can now serve as a base. The slightly negative oxygen can steal the slightly positive hydrogen attached to that oxygen, and the electrons snap back onto the oxygen to stabilize the positive charge. And what you end up with at the end of that process, what you end up with after that, and notice that this is a second proton transfer. We're moving an H+ from one molecule to the other, from one molecule to another. So that's a second proton transfer. What you end up with there is a ketone. Remember, a ketone is a carbon double bonded to oxygen with a carbon on both sides. So, you notice that we started with an enol. Here's our enol, double bond, ene, alcohol, OL, and we end up with a ketone. We did that by changing the position of a hydrogen. We took it off of one position, right? We took it off of one position and we added it to another. So that's Keto-Enol Tautomerism. And that's what you get when you do acid-catalyzed hydration to an alkyne. At first you get this enol, but that tautomerizes to this ketone by doing 2 proton transfers. Okay, let's try to draw that mechanism on a different molecule. So you see that here we have an enol. We have a double bond, so that's an alkene, and then we have the OH, that's an alcohol, so that's an enol. Okay, so if you have this enol, the pi bond is nucleophilic. There are a lot of electrons there. So if you combine that with an acid, H3O+, that's our poster child for an acid here, then the nucleophilic electrons in the pi bond can attack the slightly positive hydrogen in hydronium. The electrons would snap back onto the oxygen there to stabilize the positive charge there. Notice that that is a proton transfer. And what you get after that first step is that the hydrogen here would go on the carbon next to the carbon that has the oxygen on it. And you'll form this positive charge next to the oxygen. And because you have a positive charge next to a lone pair, you have one of those 5 resonance structures. And so this isn't the true structure. The true structure is the average of this and the other resonance structure. To find that, to warn people about that, you put these big brackets in, and you draw the special resonance arrow with 1 line and 2 heads. And then to predict that other product, you take the lone pairs that are next to the positive charge and you move them to form a bond toward the positive charge. It should make sense that those negative electrons would be attracted to that positive charge. So the structure you end up with after the other resonance structure that you would want to average with this first one looks like that. Notice that the oxygen there has 3 bonds and therefore a full positive charge. It's really important to write the charges in. They are a crucial feature of the molecule, so the structure is technically incorrect if you don't have the charges in. And they also give you important clues to how the molecule can behave or to what you need to do to the molecule. For example, this oxygen has a full positive charge which is unstable. So one thing you can do to that is get rid of the hydrogen here. You could take a base, the water, that you get when the hydronium gives its H plus away. That water can act as a base and accept an H plus. The oxygen's slightly negative, it can steal this slightly positive hydrogen, and then these electrons would snap back onto the oxygen to stabilize the positive charge there. And notice that that is a second proton transfer. And what you get after that, beautifully, is the ketone. And so we started with an enol, an OH bonded to a double bond, bonded to a carbon and a double bond, and we end up with a ketone, a carbon double bonded to oxygen, single bonded to 2 carbons. One other thing you might notice is that this water, after it accepts this H plus, turns into H3O plus. And so the H3O plus that you used at the very beginning is regenerated. And that's what makes it a catalyst. That's why this is acid-catalyzed. And if a molecule ever is used to make a reaction happen, but is not used up because it's regenerated at the end, that's a catalyst. Catalysts make reactions happen faster without getting used up themselves. And so these 2 proton transfers, along with the resonance structures, constitute the mechanism for this acid-catalyzed keto-enol tautomerism. Let's try it with another one. So here we have an enol. You can see the double bond, so that's the En, and then we have the OH, that's the alcohol. So together that's an enol. And anytime you have an enol, it will exist in equilibrium with a ketone form or an aldehyde form. So in this case, we can write this molecule like so. And this is going to be acid-catalyzed. There is also a mechanism for a base-catalyzed keto-enol tautomerism, so you might be aware of that. Just be aware that that exists. That happens in the case of hydroboration oxidation, because you remember in the second step for that, there's H2O2 and NaOH. The NaOH is a base, and so that would catalyze the keto-enol tautomerism. But in the case of acid-catalyzed hydration, you of course have acid present, and so you can do an acid-catalyzed mechanism, as we're showing here. So the alkene double bond can act as a nucleophile and attack one of these slightly positive hydrogens. These electrons in the bond, after all, have a negative charge, and the electrons in the bond can snap back onto the oxygen in hydronium and stabilize the positive charge there. So notice that that is a proton transfer. So, what you get after that step is the hydrogen adding on the less substituted carbon. And it adds on the less substituted carbon so that you would get the carbocation on the more substituted carbon, on the more stable carbon, the carbon that can borrow electrons from more carbons nearby. Now, here I just have this slightly misdrawn, sorry about that. So there's this oxygen here. So once you have that, you'll notice that you have a lone pair next to a positive charge. That's one of the 5 resonance patterns. And so you'd want to warn people by drawing brackets. That lets them know that none of the structures that you're drawing inside are the real structure. The real structure is only and always the average of all of the ones inside. And to remind them to take the average, you draw a resonance arrow between the resonance structures. That has one line with 2 heads. That says, take the average. Now, to predict the other resonance structure, you take the lone pairs and push them toward the positive charge to make a bond toward the positive charge. So, those dots, that lone pair goes to make a pi bond there. And the oxygen that you form, that oxygen that you have, has 3 bonds, and so it has a full positive charge. And you can see that that is really close to the ketone. All you have to do is a proton transfer, and the charge is reminding you of that. It tells you, this oxygen is unstable, stabilize it. So the water can come in, the water from this last step that hydronium becomes when it loses this H. The water can act as a base. The slightly negative oxygen can steal that slightly positive hydrogen. The electrons can snap back onto the oxygen there to stabilize that positive charge. Notice that this is a second proton transfer. And so, what you end up with after that step is this structure here. Notice that hydrogen is still there, it's just implied in this skeletal structure, and this hydrogen leaves, the bond turns into a lone pair, and that stabilizes the positive charge that was on that oxygen. So notice the overall transformation. We had an enol at the very beginning, and that's an alcohol, an OH, bonded to a carbon in a double bond, an alkene. And what we end up with is a ketone, a carbon double bonded to oxygen, single bonded to carbon on both sides. That's a ketone. And so this is Keto-Enol Tautomerism, a crucial term, Keto-Enol Tautomerism. And now that we've discussed it a bit, let me just quickly recap what that means. We're turning an enol into a ketone. They exist in an equilibrium. And what they are, the relationship they have to each other, are tautomers. Tautomers are molecules whose only difference is the position of an H. Notice in the enol, the H is on the oxygen, and on the ketone, the H is next door to it. This one right here. So those are tautomers. So when they change from one to the other, they tautomerize. Keto-Enol Tautomerism. Let's try one last one. You could see this is an enol. You have an alkene, the double bond, and then you have an alcohol. That's the OH. The suffix that represents it is OL, which you might recognize from molecules like cholesterol. The OL at the end of that is telling you that it's an alcohol. Or, for example, ethanol. That's drinking alcohol. It's an alcohol that has that OL at the end of the name, and that's representing that OH in the structure. So we have an enol, and anytime you have an enol, if there's even a tiny bit of acid or base in your container, then it will tautomerize. You will get a ketone and the enol existing in equilibrium. So let's say we take this enol and we treat it with catalytic acid. That's an acid that will be used to make the reaction happen, but will be reproduced in the course of the reaction. Just to get some room, extra room here. So the first step is that the double bond, the pi bond, is a nucleophile. And so it will attack anything that's slightly positive. All these hydrogens are slightly positive. They're losing electron density to the oxygen because the oxygen is really electronegative. But in addition to that, the oxygen has a positive charge that attracts the electron density even more. So all those hydrogens are slightly positive. This pi bond here is attracted to that. The electrons in it are attracted to that. They stick to one of the hydrogens, and the electrons in the bond to the hydrogen snaps back onto the oxygen to stabilize the positive charge there. And so that's your first proton transfer. After that, you end up with this molecule here. The hydrogen adds on the less substituted carbon so that you get the carbocation on the more substituted, more stable position. But you see that and you say, I have a lone pair next to a positive charge. That's a resonance structure. That's a resonance pattern. And so you warn the world that the true structure is not anything in these brackets. It's only the average of all of them. And it's always the average of all of them. So it's never any of the individual structures. It's only always the average of all of them. And to remind people to take the average, you draw that special resonance arrow with one line and two heads. To predict the other resonance structure for this, you take the lone pair that's next to the positive charge and make it form a bond toward the positive charge. The electrons in that lone pair, with their negative charge, are attracted to the positive charge in the carbocation, so they go towards it. And that makes them form a bond there. You'll notice that now that oxygen has 3 bonds. When oxygen has 3 bonds, it has a full positive charge. And that positive charge in the other resonance structure is reminding you that this is unstable. And so you can stabilize it by taking water, and this water is coming from the hydronium. After it loses this H, turns into water, the slightly negative oxygen here, because it's electronegative, is attracted to the slightly positive hydrogen. And so it steals that, the electrons snap back onto the oxygen there, stabilize the positive charge. Notice that this is a second proton transfer. So one proton transfer puts a hydrogen on, the other proton transfer takes a hydrogen off. It looks like the overall effect is a hydrogen changing places. That's tautomerism. When a molecule changes only the position of one hydrogen and otherwise stays completely the same. So what you end up with at this point is this molecule here. And you'll recognize that as a ketone. So that's this after that step. That's a ketone. You have a carbon double bonded to an oxygen, and that carbon is bonded to carbons on both sides. That's a ketone. So we have Keto-Enol Tautomerism. We started with an enol, we end with a ketone. Those are tautomers because they only have a difference of the position of one hydrogen. And we made that the position of that hydrogen change first by putting a hydrogen on a different position with one proton transfer, and then taking a hydrogen off another position with a second proton transfer. And that turned our enol into a ketone. So hopefully this mechanism, knowing this mechanism and drawing this mechanism, will make more sense of how you can do this reaction like acid-catalyzed hydration that you learned about in the alkene chapter, which adds H and OH, and how that can ultimately leave you with a ketone after you add the H and the OH. At first, getting the enol, but then it tautomerizes. That's what happens if you have acid-catalyzed hydration, where the oxygen goes on the more substituted carbon. If you have hydroboration oxidation, which is anti-Markovnikov, that means the oxygen goes on the less substituted carbon, this one on the end, but you still get the tautomerization and the OH turns into a double bond to an oxygen through a similar mechanism. It's just base catalyzed. So hopefully this video helps you a little bit with drawing the mechanism of an acid-catalyzed keto-enol tautomerism.